Now we'll look at an example of a line integral of a scalar function in 3 dimensions. So we start with the same ingredients. We start with a parameterization of a curve in 3 dimensions. We start also with a scalar function of 3 variables. And we want to find the line integral of this function along the curve with respect to arc length. So there's the setup. That's what we want to find. The integral along the curve C of f of x, y, z with respect to arc length ds. ds we can unpack. ds unpacks as it did before, r prime of t in magnitude dt. So that's what ds has unpacked into. And there we've expanded out what r prime of t is. But we could also keep it in this nice shorthand form, and that is, it's just the integral of f evaluated on the curve times the magnitude of r prime of t dt. Let's have a look at an example. So we want to find the mass of the helix if the density at a point is given by that expression there, x squared plus y squared plus z squared equals 2. So the idea is we've got this helix sort of spiraling around, and we're interested in between 0 and 2 pi, when the t value is between 0 and 2 pi. But the density is changing. The density is depending on x squared plus y squared plus z squared. In other words, the density is depending on the square of the distance the point is from the origin. The further away it gets, the more dense this helix is becoming. So how do we find the mass? Well, the mass in general, if the density was constant, it would be density times the length of the curve. The problem is the density is varying. The density is changing as I go along the curve. So if I chop my curve up into little bits and think of the density as being constant along a little segment, then I can take my density, which I'll write down as rho x, y, z at a point. I'll multiply it by the little tiny length of the segment I'm getting, and then I'll sum up over all of these. But the sum in this case over all of these, since these lengths are going to 0, becomes an integral. So we are integrating over the helix. And so that is the mass. That's what we want to compute. So there you can see we just came up with the integral of a function with respect to arc length on our own, just given the context of the problem. And so that's precisely the integral that we introduced above. And we know how to evaluate this. How we evaluate it is we integrate putting everything in terms of t now. We use the parameterization to put everything in terms of t, kind of like a substitution. We substitute x, y, and z all in terms of expressions for t. ds becomes an expression in terms of t. So here it is. Our curve is given up above. X is cos of t, y is sine of t, z is t. So what is rho going to be? Rho is going to be x squared, so that's cos of t squared, plus sine squared of t, plus t squared. So that's our density function with everything plugged in terms of t. ds becomes the square root of dx dt. dx dt, well, x of t is cos of t, so its derivative would be negative sine of t squared, plus the derivative of sine of t is cos of t squared, and the derivative of z with respect to t is just 1 squared, and that becomes dt. So basically I've used this to plug in everywhere and used the fact that dx dt is equal to negative sine t, dy dt is equal to cos of t, and I use dz dt is equal to 1. Now we can do a little bit of simplification before we evaluate. Cos squared plus sine squared, that's 1, so what's out front here is a 1 plus t squared. And then I've got a sine squared plus cos squared under the square root sign, plus another 1, so I have a 1 plus 1 there. Or in other words, this is square root of 2, the integral from 0 to 2 pi, 1 plus t squared dt. And so that becomes then the square root of 2. The integral of 1 is t. The integral of t squared is 1/3 t cubed. And that's going to go from 0 to 2 pi. So we get root 2 times 2 pi plus 8/3 pi cubed. And so there is our final answer. That is the mass of this helix given that density function. Alright, so that's it for this example and our extensions into 3 dimensions for integrals of scalar functions with respect to arc length. In the next video, we're going to look at the other type of line integral we can get, and that is an integral of a vector field along a space curve. So we'll see you in the next video.